Hi there, welcome back. Today is the day of the value at risk and the expected shortfall. We will see that the value at risk from a statistical point of view is nothing more than a quantile of the loss distribution, while the expected shortfall is a conditional expectation, is the average of all the losses above the value at risk of the large losses. It's an average of large losses that gives us a measure of what we can actually expect from our portfolio in terms of losses. The fact that we call them value at risk and expected shortfall is just due to the fact that in finance, financial guys like to give fancy names and strange definitions to common objects. It's a sort of attitude, it's if you want, it's a selling strategy. But we will analyze both measures, trying to understand when they work, when they don't, and if they can exhibit some nice properties like coherence. We will have several exercises in this class. Some can be very boring. I can totally agree with you, but they are important to understand some of the characteristics of these measures. Starting from next time, actually, we will combine all the things that we have seen until now, all these very simple tools, if you think about them, to see how we can actually start managing risk in the different declinations of risk that we find in a large financial institution: market risk, credit risk, operational risk, and the rest. Enjoy! Today we introduce the last set of basic tools that, starting from next time, we will use to actually deal with the major type of risks we can play with as risk managers. These tools are the value at risk, which is the first topic that we consider today, and the expected shortfall. These are two quantities that probably you have not seen in other courses, so probably the first novelties. And their use in risk management is actually very important and very discussed. It's important because we will see, for example, when we consider market risk and credit risk and also operational risk in the Basel framework, that actually banks and large financial institutions are obliged to use these measures. So there is no choice. They have to, otherwise they cannot operate on the market according to the corresponding regulator. So, for example, in the Netherlands, the Dutch National Bank. But at the same time, over the years, we have discovered, or at least practitioners have discovered, that these measures have their own problems. So in the academia, it was known. There was a big discussion in the early 2000s when actually the guys in Basel were thinking about using the value at risk. And people in the academia were telling, be careful, because this type of measures seems nice properties, but in reality, it has a lot of problems. Now, what we will do together is try to see both sides of the coin, so the positive part and the negative part. I'll try to be neutral in the sense that I will try to show you that actually the value at risk in several situations can be useful, but it's a measure that personally I don't like for the many problems it has. By the way, when you use a measure and the value at risk, for example, was considered and was criticized as one of the big big causes of the last crisis, because it was massively used in the different models, my point is that it's never the fault of the measure you use. A measure is a statistical tool, a probabilistic tool. It's just a number at the end of the day, what you get. The problem there is never the measure, it's you using the measure. So if something does not work, it's your problem, it's not the problem of the measure. Now, the value at risk is the way in which financial guys call something that you probably heard of, that are quantiles. If you're a statistician, value at risk is a quantile of your loss distribution. Now, value at risk is the measure that in principle answers an important question, which is how bad can things get? So if you're investing, you want to know how bad can things get, in the sense, how bad can your losses be. Now, it's a measure that if you want to introduce, you need to specify a little bit better the question by introducing the following. We look with the probability alpha for the value capital V such that over a given time horizon that we call capital T, we will not lose more than that value with that probability. Now, the confidence level is the alpha there. The valid risk is nothing more than that capital T, and the capital T is this time horizon that we will define. So every valid risk requires the definition of a loss distribution, a time horizon, and a alpha level. So what we will call the confidence level. Now, the valid risk can be applied and computed to different loss distributions. The loss distribution is the distribution that tells us how the losses are distributed in our portfolio or in our investment. And we have essentially two types of distributions. We can have the distribution of gains or the distribution of profits, in which profits are positive and losses are negative. So if I invest in something and I have a profit of 1 million, it's plus 1. If I have a loss of 1 million, it's minus 1. This is the typical profit and loss distribution or gain distribution that you have, for example, when you invest or in asset management, portfolio management. The distribution of losses, conversely, is the distribution in which the losses are positive and the profits are negative. This is typically the distribution that we use in risk management. So since we are interested in hedging losses, in order to simplify a little bit the formulas to get rid of all the minus signs, what you do, you just switch the distribution. So if you have a profit of 1 million, for you is a loss of minus 1 million. And if you have a loss of 1 million, for you is actually a loss of 1 million, so plus 1 million. So it's just a matter of convention. But in risk management, this is essentially the loss distribution that you use. So losses positive, profits negative. It's very important because under the first distribution, that is to say the gain distribution or the profit and loss, what you have that your valid risk will typically lie on the left-hand side of the distribution. While if you consider the loss distribution, the valid risk will typically lie on the right-hand side of the distribution. So instead of the left tail, you will play with the right tail. If you want to give a more formal definition of valid risk, it's just nothing more than the definition of a quantile, the alpha quantile of your distribution. Now, what is a quantile? When you have whatever type of distribution, okay, you have this distribution, and at a certain point, you know that if you integrate under this curve, which is the density of your random variable, you are essentially getting the probability of being, for example, smaller than equal to a given value. So if this is the f of my random variable capital X, what I have here, if I take this area here, I'm taking the probability that x is smaller than equal to small x, where small x is a value, like 10. Okay? Now, typically, we're used to say what's the probability that I will be below x. Now, we can also ask the following, the opposite, sorry. I can fix the probability. I can say I want a probability of 90% and find the corresponding value. So if I fix the probability and I look for the value such that all the other observations will lie below that value is a quantile. And that's essentially the valid risk. Now, if you define the valid risk at a level alpha, essentially you are looking for the smallest value, small l, which is, in general, to simplify, a real number, such that the probability of observing a loss which is larger is at most 1 minus alpha. That is to say, the probability of being below is alpha, and the probability of being above is 1 minus alpha, because they have to sum to 1. Okay? So, if you want to say that in words, as you see on the slides, the valid risk is the loss value for which the probability of observing a larger loss, given the available information, and given the available information is extremely important as a sentence, is equal to 1 minus alpha. In the small drawing that you see on the slides, we're essentially looking at the tail that is the 1 minus alpha. That area there accounts for the probability 1 minus alpha. The white area on the left-hand side, on the contrary, will be alpha. That definition is the general definition if you play with both discrete and continuous variables. If you play just with continuous variables, so if you introduce just continuous variable, then you can also put the equal sign, but just in that situation. Otherwise, you can have some tricky limit situations, and not in most of the times, but still, it's important to recall that the equal sign should not appear there. Now, as I was telling you before, the valid risk relies on two main quantities that need to be defined before starting computing the valid risk. One is the loss distribution, which is not a quantity, but is a set of quantities. So it's the distribution representing the losses and the profits as negative losses of my portfolio, and the alpha value. Okay? Now, for what concerns the loss distribution, we will see that there are mainly two types of loss distributions: theoretical loss distributions and empirical loss distributions. Now, the empirical ones are just those that you can estimate from actual data. So you have, for example, the historical data of the performances of your portfolio. You have your data set stored somewhere. You can take an approximation of the loss distribution from those data, and you can use that information, the empirical loss distribution, to compute the bar. In other situations in which maybe you don't have enough data, maybe you think you have developed a model that you trust a lot, a model that you like, or maybe it's a model that is imposed by the regulator, you don't have actual data, so it's not a distribution that you can actually find in the data you have, but it's a distribution that you derive theoretically from your model. We would see that very often there are models in which at a certain point the distribution is a normal distribution, a log normal distribution, and all these kind of things. The alpha value, on the contrary, is this confidence level that you have to define, and it is something like 99%, 95%, 99.9%, and it's a value that typically is coupled with a time horizon. So I want to know the valid risk at 99% level over 1 day, over 10 days, over 1 year. Now, what I have, for example, underlined there, the 99% of 1 day that you can represent as 0.99 or 99%. Okay, this is just my thing. These are, for example, one value of the VAR, which is commonly used in market risk. If, on the contrary, you are interested in a value of valid risk which is commonly used in credit risk, that would be this one, the valid risk over 1 year. Because as I was telling you last time, market risk and credit risk tend to have different time horizon because of the characteristics of the different portfolios we play with. Now, the values, the most common values are from 90% onwards, so 90%, 95%, 97.5, 99, 99.9, 99.9, for example, is called the worst case scenario. So you really want to know what is the value such that only a very, very small amount of losses are in principle above. Most of the times, the alpha level is provided by the regulator. So if you take the Basel rules, you will find you have to estimate the 95% valid risk, the 99% valid risk for this type of risk. Clearly, as a risk manager, for your own purposes and for your own analysis, you can define all the time horizons and all the levels that you want. So if you are interested in the 87% valid risk, feel free. Now, suppose that there is a one-year project, okay, and all the outcomes between a gain of 80 million and a loss of 20 million are considered to be equally likely. Now, the idea is, what is the one-year value at risk for alpha equal to 0.9? Now, the idea here is to try to understand what the text of the problem is telling you. You know that you have a one-year project, so essentially you are computing the value at risk over a one-year time horizon. The alpha is 0.90, so we have this information. What we need to understand is the loss distribution. Okay? In this specific case, we have some information because we know that loss distribution is bounded between a maximum gain of 80 million and a maximum loss of 20 million. Okay? So if I want to try to draw this loss distribution, I can actually do that quite easily. So the first thing that I have to remember is that for me, profits are negative and losses are positive. So if I set 0 here and I write everything in million, okay, otherwise 2 million would be somewhere I don't want to reach. This is 10 million and this is 20 million. That's the maximum loss. Okay, so my distribution will necessarily end here. On the opposite side, we have the profits, and profits go from 0 to minus 80. Let's say that minus 80 is here. Okay, so first of all, I have to look at the signs, and since we are risk managers, with which profits are negative, losses are positive. Now, the second thing is that all the losses are considered equally likely. It means that between minus 80 and 20, all the different losses, like 11, 12, minus 0.5, minus 18, are equally likely. They have the same probability. So what's the distribution that we're essentially assuming here? Something very simple. It's the uniform distribution. So we have a distribution that assigns the same mass to all the possible values that lie between minus 80 and 20. And this area here essentially sums to 1. Now, what we want to find is the value such that 90% of the observations are smaller and 10%, 1 minus 0.9, are larger. Now, in this specific case, it's very simple. The distance between minus 80 and 20 is 100, okay? So every 10 in absolute value, every 10 million of losses, we have a 10% of our probability. So it's not particularly complicated to see that the 90% bar is this value, is 10 million. So 10 million will be the value such that 90% of the losses are smaller, and again, a profit is a negative loss, so it is smaller, and between 10 and 20, I will have 10%. Now, starting from today, this is not the most difficult exercise. We will have a little bit more cumbersome exercises, but starting from today, on the course platform, you will have this. So you will have, it would be difficult to let you, now, I can assure you that there is an audio. Maybe it's not working here because of, University of Technology, but there are videos.
Is represented by a uniform distribution over the support.
Okay, so you
80,
find
20.
You can see my
Since we have
hairy head, my hairy hands, all the things. You can listen to my voice. You can hate my voice by listening that several times if you need that. But in a sense, you have a prototype of the different exercises there. So if you're not in class or you miss something of my explanation and you are shy and you don't want to ask, there you find it again. Okay, so that should help you to understand a little bit the exercises, at least the most difficult ones. They are not difficult, they are boring, which is another thing, but that's the type of things. We are sad people in risk management, so there is no happiness for us. Now, the valid risk, we will see, can be computed empirically. Already here, if you want, okay, we were assuming a distribution, but let's assume that that was coming from empirical data. We have ways to compute that, and we will do that in a minute. But there are specific situations, and once again, the normal distribution is one of the situations, one of the most common situations in which the valid risk, if you know that the distribution is normal, or you know that your data can be approximated by a normal distribution, then you have a closed form solution for the valid risk. So if you assume that your losses are normally distributed with a mean mu and a standard deviation sigma, and you fix an alpha level, obviously between 0 and 1, so 0.9, 90%, now the value at risk at the alpha level is equal to mu plus sigma plus plus times phi to the minus 1 alpha. Now, what is mu? I don't think there is nothing to say about that. It's the mean, okay? Sigma is the standard deviation, or we solved volatility, so it's volatility. And we have the novelty. If you don't remember that from your courses in statistics, is this phi to the minus 1. Phi to the minus 1 at level alpha is the quantile function of a standard normal. Now, a standard normal or a standard Gaussian distribution is that particular distribution, that particular normal distribution that has mean 0 and standard deviation 1 or variance 1. It's exactly the same. So, if you are considering the function phi to the minus 1 alpha, essentially you are looking for this value. I have my normal distribution. Assume that this is the standard normal distribution, which is centered in 0 and whose standard deviation is equal to 1. And I say, okay, I fix an alpha level. The alpha level for me is 90%. So I will look for the area under this curve that accounts for 90%. Let's say that this area stops here. So this is 90%. So that this part here is 10%. Now, the quantity phi to the minus 1 alpha will just give me this point here. This is 5 to the minus 1 of 0.9. It's nothing more than the inverse function of phi, which is another way of calling n. So when you write a normal 0, 1 in statistics, this is equivalent to phi 0, 1. Okay, so you are just inverting that function. Not the curve that you see there, because this is the density, but the CDF that you may remember is this type of curve. It's the cumulative distribution. This is the density. Okay, so that's what you do with the valid risk under normality. The normal distribution is one of the cases in which you have a closed form, which is very simple. You see that essentially you have three quantities, mu, sigma, and the quantile. Now, the quantile will just depend on the alpha level. So if you fix the alpha level, it's a number. So we will see that if you fix the alpha level at, say, 95%, that quantity is a certain number. If you fix that at 99%, is another number. And they are always that number. What really changes are mu and sigma. Mu is the mean. Very often it is taken to be close to 0 or rescaled to be equal to 0. Sigma is your standard deviation, your volatility. You remember I told you that the value risk in case of normality depends on volatility. And you see why, because sigma is there. So if your estimate of volatility is not reliable, your estimate of the value risk under normality is not reliable. Other distributions that have similar, for example, equations for the var are the t. You may remember that the t distribution is this strange distribution that you introduce, for example, when your sample size is not big enough. It is a distribution that in the limit will tend to behave like a normal, but at the same time it has nice properties for what concerns the tails. It's a tricky object, but you see that the result is essentially the same. You substitute the quantile function of the normal with the quantile function of the t distribution. But we will not enter into much details with the t, at least not at the moment, maybe for other topics. Now, assume that losses in a portfolio are well approximated by a normal distribution with mean 2 and variance 4. We ask ourselves, what is the var at the 95% level and what is the var at the 97.5 level? Now, again, these exercises are meant to understand the rationale behind how it works. Then obviously, when you are a risk manager, you perform your computations, you are not using the standard normal tables, and you are doing everything with your computer. But still, understanding what is happening in your code is always quite important. And by the way, we cannot use during the exam the computer, so we have to do everything the very old-fashioned way. But nevertheless, is useful if one day you are a risk manager and there is a power outage, there is a blackout, and you still have to compute the var. Okay, so normal distribution with mean 2 and variance 4. So we want to apply the formula that we have seen in the previous slide. That formula is mu plus sigma times the quantile function of a standard normal. So let's rewrite it. The var alpha is var alpha. And notice that we write var with a capital R to distinguish that, for example, from the variance. Another way of writing var is using the at, because you don't want the var to be confused with the variance. They are two different things. And believe me, I saw, it happened to me when I was a very young consultant a few years ago, to see the chief risk officer of a relatively important bank confusing the two things, which is quite scary if you have a bank account in that bank, and then the next day you move your bank account to another bank. So the function is mu plus sigma phi to the minus 1 alpha. This is what we want to apply. Now, let's read the text. So what do we know is that the mean is equal to 2, okay? So the mean is equal to 2, plus sigma is the standard deviation. There we have a very complicated variance of 4, for which we have to take the square root. So square root of 4, it's another 2. And then we have to apply the quantity phi to the minus 1 of, for example, for the first question, 0.95. Okay? Now, how can we do? If you have a computer, I will show you in a minute what you can do. But if you don't have a computer and you have, for example, the normal table as it happens during the exam, how do you use that? Now, in these normal tables, what they have done, they have tabulated the critical values and the probabilities of a standard normal. So it's a normal, 0, 1. What do you read in that table? You see that there is a quantity Q on the upper part on the left. So there is a Q, and then you have one column 0, 0.0, 0, 0.1, 0, 0.2, 0, 0.3, and the first row 0, 1, 2, 3, 4 until 9. Okay, how do you read that? This value, if you combine the value that you find in the first column with the value that you combine what you find on the first row, you're essentially finding a critical value. Essentially, it's the quantile that we will need. So what does it mean? If I take, for example, the value 0, 0.0 and the first 0 on the first row, this is the quantity such that if I read how the table is derived, such that 50% of the observations are smaller and 50% of the observations are larger. Does it make sense? Yes, because if I take a normal distribution, which is standard, the mean is 0. It's symmetric, so the probability of being below the mean is 0.5. The probability of being above the mean is 0.5. What are the numbers within the table? The number within the tables are decimals. So you have to read, for example, the first number, 5,000. It is 0.5000. Okay, so it's 0.5. The second value, which is 4960, you have to consider that there is a 0 point in front of that. So it's 0.4960. Now, imagine that I want to find the 95% value at risk. The 95 value at risk is that value such that 95% of the observations are smaller and only 5% are larger. In that table, I have the probability of being above a given value. So it's 1 minus alpha for us. It's the value 1 minus alpha. So what I have to do, I have to surf through the table and look for the combination of the first column and the first row such that the value I find in the table is more or less 5%. If you do that, you will find that there are two values in the table that are very close to 0.5. And these are the value 0.505, so 0.0505, and the value 0.0495. Now, for the sake of this course, you can take each one of them. It's close enough. Or, if you want to be very sophisticated, you can take a midpoint. What's a midpoint? If I choose 0.0505 and I look at the combination of the first column, first row, I have that the first column is 1.6 and the first row is the value 4. So that the critical value corresponding to a probability in the tail of 0.0505 is 1.64. If I compute the value such that the probability to be in the tail, the 1 minus alpha, is 0.0495, that value is 1.65. If I want to take something in between, I will take the value 1.645, which is in between 0.64, 1.64 and 1.65. Actually, if you take your computer and you compute that, the value you will get, it's very, very close to that, will be 6448. So this is what we have to do. Once we have that value, we plug in it here, and we make our computation, 5.29. That is our 95% value at risk. If I want to do at the 97.5 level, it's exactly the same idea. So this number does not change, this number does not change, this number will change, because instead of 0.95, now I'm consider the quantity 97.5, such that the probability of being above, that is to say 1 minus alpha, it is what? It is 2.5%. Okay? So what I have to do, I go in the table and I look for something that is close enough to 2.5%. So let's go there and let's surf a little bit. So this is 2.87, 81, 74, 2.5. because this is 0.0250, so this is 2.5%. Okay? 2.5% corresponds to the value 1.96. So 1.96. This is actually the value that I have to input in my formula in order to compute the valued risk. This value in the formula will give me a valued risk of 5.92. Okay? So this is how you use the standard normal tables. Now, we know that the historical one-year loss distribution of a portfolio of loans in $1 million is well approximated by a normal 10-25. So 10 is the mean and 25 is the variance. What is the 95% valued risk and what is the 98% valued risk? Now, there are different possibilities. I can take the table again, do that as an exercise, or you can use, for example, computer code. If you want to use R, you use R. If you want to use Python, you use Python. If you are particularly advanced, you can even use Excel. So it's not a problem to estimate these kind of things. So what you have is that the critical value under the normal distribution, the standard normal distribution, at the 95% confidence level, the precise value you see is 1.6448. You agree with me that this value is very close to the value we have used, that was 1.645, that we could just obtain from the tables. If you want the 98%, that would be the value, and what you clearly see is that the more you move yourself in the tail by taking a higher quantile, the higher the valued risk. Makes sense. So you are pushing in the tail. So you are going there. Okay, questions so far? Now, let's see another exercise, which is a little bit different, and in which we should really get our hands dirty in the computation. Nothing particularly difficult, but it is important to understand a little bit how we have to proceed empirically when we don't have a formula like this one. Okay, so when we just have the data. Again, I repeat, no risk manager will do that manually. They will use their computer, but we try to understand what the computer does. And you will see that at a certain point, there will be a very important difference between the result that we could get if we were statisticians and the results that we get if we think as risk managers. We will see that this is already one of the first situations in which there are conventions in risk management that are different from the standard way in which a statistician would operate. By the way,